Hello, I'm Anna Mackay, and in this video we're doing rules of integration. So integration is essentially the reverse process of differentiation. We've got a list here of some of the basic rules. You'll notice this symbol here is an elongated F, if you like, without the line, or an S symbol. My understanding is that it comes from a German letter for what used to be a double S, and Leibniz was the first person to identify that. And the S idea is that it was used for a summation of infinitesimal parts. Don't worry too much about that. Let's have a look at some of the elements that are consistent here. There's this plus C that's on the end of each of these rules. Just cast your mind back to differentiating something. So if we had our function here, ignore that, and our function was x cubed, what would the derivative of that be? Well, that's where you bring down the power and lower the power by 1. So we'd have 3x squared. Well, what would the derivative of x to the power of 3 plus 7 be? Well, the derivative of the x cubed would still be this, and the derivative of the constant would be 0, so it's disappeared. So if integration is going from the derivative back up to the function, the integral here is, you notice that, so if we had x squared, we're going to raise the power from a 2 up to a 3, and then there's a constant that could be added on the end, because when you're doing the differentiation process, any constants disappear. So when we integrate, we have to take that into account for all the different combinations we could have. So I'm going to do an example of each of these 6. So using basic integration rules, find the following indefinite integrals. We've got another video on definite integrals at another point. So this first one here, when you have a constant, having a look at this first rule here, the integral of that is where you add an x onto it and a plus c. So our answers for that is 5x and plus c, the integration constant. If you ever want to check these things, you would consider 5x plus c is now your function. So, and therefore, what would the derivative of that be? That's where you lower the power by 1. So lowering the power of x here by 1 leaves us just with the 5. And then when you differentiate a constant, it disappears, it becomes 0. So now our derivative is 5. So that's essentially what's happening here. The function that you see there is the derivative, and we want to integrate that to find the function. The purpose of the dx there is saying, you may be familiar with the dy by dx, the change in y and the change in x. This is implying that apply those rules to an x variable. You'll see over on this third one here, we have a t, and so we use dt. So it's essentially just apply the rules to the variable that's stated in the d section there. Number 2, the part B here. This roughly matches rule number 2. The difference is, though, it's a fraction. So let's rewrite that first as without the fraction. So I'm going to keep the integral sign because I haven't applied the rules yet, and I'm going to write it x to the power of -4 dx. And now I'm going to apply the integration rules. So what happens is that -3 is going to stay there. Then we have x. Instead of to the power of -4, we're going to raise that power by 1. So from -4 becomes now -3. Raising it by 1 means increasing it by 1, not becoming -5. So it's -3, and then you put the whole thing over that new power, and plus c. You have to always add on that constant, and rearranging that, tidying up essentially, those -3's cancel out, so we're left with x to the power of -3 plus c. Once again, you could always check that. If this was now your function, x to the power of -3, what's the derivative of that? You lower the power, bring the power down the front, lower the power by 1, and that constant would disappear. And then, as you can see, that is the same as the function you first started with. Part C here, I'll use this as an opportunity to mention, I guess, a sub-rule here, that what's the best way to describe them? Common factors or coefficients here, they can be removed out the front of the integral and won't have any effect. There are proofs for that in your textbook. And we would be left with this function here. So that 5 essentially could be multiplied back through, and that factor of 5 is not going to have any impact on the rules that we're going to apply to the integration. Now this now looks like rule number 3. So always be on the lookout when you have the variable on the bottom to a single power. Over here it was to the power of 4. That's to the power of -1. If you increase -1 to up 1, it becomes 0, and that creates a whole world of problems. And so that's when we have our ln function. So the integral of this is now, when we stop writing the integral sign, we have 5 ln of t plus c. Two steps here. Finding the integral first of an e to the x function. As you remember from differentiating e to the x functions, the derivative is the same, so therefore the integral is going to be the same. So by integrating this, that -3 is not going to change. We copy and paste the e to the x and add in plus c. Don't forget that. Now the second part here says, now find f of x given that f of 1 is equal to -4.15. So I like to write out the fact that f of x is this function here, -3 e to the x plus c. And now I'm going to substitute in these facts and solve for c. So f of 1, I forgot to put my equal sign in above, f of 1 is equal to -3 e to the power of 1, because where I see an x I'm putting a 1, plus c is equal to -4.15. I'm going to rearrange that to solve for c, and that approximately comes out to be 4. So summarising that, it did say to find f of x, so don't just leave it there. Our function therefore is -3 e to the power of x plus 4. So now we know that plus c, that integration constant, and the only way we were able to find that out is with a fact. So a piece of information of 1 point on the graph where you have an x and a y coordinate, that will allow you to solve for that third variable of c. And now we have the full function, and its derivative function would be -3 e to the x. Part E here, it's starting to look a bit more complex. You might be thinking to yourself, oh, okay, it's a fraction. I wonder if it's sort of a quotient rule or something like that. Well, in our course here, Year 12 Maths Methods course, we don't have a set of rules for being able to integrate complex functions like this. The type of integration that we're doing is called term-by-term integration. So currently that's one term, but having the denominator as it is means we can actually split the terms in the numerator up. So I'll show you what I mean by that. So I'm going to split the denominator there over each of the terms, keeping the dx at the end. Just going to tidy that up a little bit first. Those factors of x can cancel out on a couple of them. The next step is, and you don't need to show this most times, I'm just going to split that integral across the 3 to show you how the rules work. So the first one is the integral of 2x cubed, and then we put dx on. And then we add on the integral of x squared dx, and subtract off, I'm actually going to bring the 3 out the front and do the integral of 1 on x dx. So essentially the type of integration that you're doing means that you can split each of these and apply the integration rules to each term. Usually we just do this term by term and we don't show the fact that we're doing this. So I'm just going to show it this once, and then we integrate each of those terms. So we have the 2, x to the power of 3, you raise the 3 by 1 to get a 4 and put it over the 4. Then you add on x squared, you raise the 2 up to a 3 and put it over the 3. And being on the lookout there, 1 on x, the integral of that is ln x, and we must always add our plus c. And you can just leave it like that, but I'm just going to tidy it up, essentially that first term there, tidy up the denominator. To our final answer there. Excuse my error at the bottom, having issues writing on my iPad that low on the screen. Next. Once again, this function here looks like a single term, but we can split it into multiple terms here. So the first step is that x squared can go over root x, and we're going to subtract off 2 on root x and put dx on the end there. Now I'm going to tidy up the square roots. I'm going to write them with their powers. So we have x squared on x to the power of a half, subtract 2 on x to the power of a half dx. Once again, using our index laws, we end up with x, 2 subtract a half, which is x to the power of 3 on 2, subtract 2 x to the power of negative a half dx. And now we're in a position to start applying the integral rules. So the first term there, it is to the power of 3 on 2. I'm going to increase that by 1, which gives me 5 on 2. And I'm going to put it over that power, 5 on 2. The next one is 2x to the power of, it was negative a half, increase that by 1 to get positive a half, and put it over the power, and plus c. I'm going to tidy this up a little bit more. So the first term, the 5 on 2, as you know, flips to become 2 on 5, and that power 5 on 2. I'm just going to do a little side note over here. The x to the power of 5 on 2, let's split that up into some whole numbers. So we have essentially x to the power of 4 on 2 and x to the power of a half, and x to the power of 4 on 2 is x squared, and the x to the power of a half is the square root of x. So that's actually possibly a neater way of writing 5 on 2 if you don't want fractional powers. So I'll put that back in my answer, x squared root x, and the other one, we have this negative 2 divided by a half. So the half flips, so we're going to get negative 4 square root of x plus c. The question is, do I have to tidy that up? So if you were to write that in a test or an exam, this line here, and leave it like that, that's perfectly correct. My advice is if you don't have to go on and use it in another part of a question, leave it like that so you don't run the risk of making mistakes as you tidy up. If you do have to do more parts of a question, chances are if it's tidied up like this, it's going to make it easier for the rest of the question that you're going to do. So always make sure you read the question to see what it's asking. And one more, a trig function here. So we have a sine and a cos here. The integrals of those, so 2 sine x. Have a look down at your rules. If you have an integral of sine x, the integral is negative cos x. As you'll know that when you differentiate cos x, you get negative sine. So if you don't have the negative in the sign to start with, you've got to compensate for that in the integral. So our answer for this is, stop writing the integral sign. We have the negative, the 2 stays there, and we have cos of x, and subtract. And the integral of a cos x, having a look down here, is sine x. Don't forget your plus c. And the second part asks us to find f of x given this fact that f of 0 is equal to 4. So I like to write out the function. You could just tack on f of x onto the end of what we just wrote, but I find it easier to write this all out because then when you substitute in that x value, it's very clear where it's going to sit. For example, right here, f of 0 is equal to negative 2 cos of 0. So where we see an x, we're substituting in a 0. Sine of 0 plus c is equal to 4. Now, using your knowledge of the unit circle, when we have 0 degrees, we're essentially over here. Cos is the x value in that, so our x value out there is 1. So we've got negative 2, this becomes 1, so it stays as negative 2. Subtract off. Sine of 0 is the y component here, which is 0, so we're subtracting off 0, plus c is equal to 4. Rearrange for c, we're going to get c is 6. So finish the question, we're asked to find f of x. So writing that completed thing out, negative 2 cos of x minus sine x and plus 6. Okay, join me in the next video for 4F integrating functions of ax plus b. Give it a thumbs up, subscribe to the channel. Thank you.